Okay, in this video we're going to be looking at logical operators. We're going to start off by looking at the AND logical operator, which means that both switches must be on in order to get a positive output. So we're going to use a light bulb analogy to start with, and then we'll look at truth tables and how that relates to computing. So with both of the switches off, obviously there is no output, so the light is not on. If we switch one of those lights on, then there is still no output. If we switch the other one on, again, still no output. It's only when we switch both of them on that the output is positive, so the light switches on. So this is an OR logical operator, and in this case either of the switches can be on in order for the output to be on. So the first switch on, the light is on. The second switch on, the light is on, and with both of them, then the light is also on. Okay, so in computing we're obviously not going to be dealing with light switches and light bulbs, we're going to be dealing with Boolean, so we've got zeros and ones. So a 0 is off and a 1 is on. So if we're looking at doing this for an AND logical operator or an AND gate, when we have two zeros it means that they're both off, so it's therefore off. And as with an AND we need both of them to be on. When only one of them is on, so output B, we are still off, the same as if it swaps to output A. However, when they are both on, then the output would be on or a 1. So a truth table for an OR logical operator is obviously when either of the two inputs is on. So when they're both off, it is of course off, but when B is on, then the output is on, and when A is on, the output is on, and when both of them are on, the output is on. So what's the point in this, I hear you asking? There are practical uses for this. So logical operators can be used in control systems. So if we look at how an OR could be used, it might be that in order to close the windows on a commercial greenhouse, one of the following conditions has to be true. So if the wind speed is over 12 kilometers an hour, then the windows have to be closed. And also if it's raining, then the windows need to be closed. So it doesn't have to be both, it can be either or. So an example for an AND logical operator, it could be that a sprinkler needs to be turned on in a field if the temperature is above 25 degrees and it hasn't rained in the last 5 days. That is an example of an AND because both of them need to be true. Okay, now you know that these aren't completely useless, we'll have a look at a couple more logical operators. So this one is called an exclusive OR. And what this means is that if both inputs are off, then the output is off. If one of the inputs is on, so in this case B is on, so that would be a positive output, and in this case 1 is on. However, if they are both on, then the output is off. So it's only if one of them's on. If both are off or both are on, then the output is off. So the final logical operator is a NOT. This works where if the input is not present, it's off, then the output is present, so it basically swaps over, and the same if the input is present, the output is then not. So it just swaps from being on to off, no matter whether it's on or off originally. Okay, hopefully you now all understand how an AND or an OR, etc. works. We also need to be able to write them down so that we can do some algebra with them. So if we're saying AND, so we could say it's got to be A and B, so input A and input B. The way that we'd write that in algebra notation is A dot B. If we're doing the same but we're doing it with an OR, then we would do A plus B. And if we're doing an exclusive OR, then we would have to do A, a circle with a cross in it, and then B. And finally, if we're saying not A, because we're only going to have one input for our not, then we have to do the letter A, and it has a line across the top of it. Okay, when we come to do some further equations later on, there's a method that really helps simplify things. So if we're thinking initially about an OR logical operator, which obviously uses a plus, so it would be A plus B, if you actually think of that plus as being a mathematical plus, it works quite nicely to find out the answers. So if we have our inputs, we've got A and B. So initially A is 0 and B is 0. If we add 0 to 0, then of course you get 0. If A is 1 but B is 0 and we add them together, we get 1 because 1 plus 0 is 1. And vice versa, if A is 0 and B is 1 and we add them together, then we get 1. The only time it gets confusing, and it is only on using an OR gate, is if we have a 1 plus a 1. Now we know, because we know what an OR does, that because at least one of them is on, that the output is going to be 1, which isn't 2, which would make sense. The way you can think of this is that the 1 is actually something. So something plus something is something. Okay, now that's the only time it gets weird, but it does work. So if we move on to thinking about how an AND logical operator would work, obviously we use a dot, so A dot B is A and B. If we think of the dot as being a multiply symbol, sort of a multiply in the mathematical sense, again, then it works out quite nicely. So if we have our two inputs again, A and B, and we have 0 dot 0, so they are both off. If we multiply them together, so of course we are swapping out the dot for a multiply, 0 times 0 is of course 0. If we have a 1 and a 0, 1, 0 is 0. And if we have 0 ones, then of course we have 0. Then 1 times 1, so we've got 1, 1, that would equal 1. So you can see that it works out quite nicely with swapping the full stop to a multiply. Okay, using that method we can start to create some rules. So if we go back to the OR logical operator, we know that 0 plus 0 equals 0. And if we have 1 plus 0, then that's going to equal 1, and vice versa. And if we have 1 plus 1, then again that equals 1, because something plus something is something. So we can start to create some algebraic rules. So if we say that we have A, which can be anything, either a 0 or a 1, and we add that to 0, then we know that the answer is always going to be A. Now the reason for that is because if A is 0, 0 plus 0 is 0, so A was already 0, so that makes sense. And if A is 1, then 1 plus 0 is 1. So again, A was originally 1, so that rule works. Likewise, if we say that A plus 1 is always going to equal 1. Now the reason for that, again, if A is 0, then 0 plus 1 is 1. And if we say that A is actually going to be 1, then 1 plus 1 is 1. So that rule works. So furthermore, we can say that A plus A is always going to equal A. Because if we say that A is going to be 0, 0 plus 0 is 0. And if we say that A is 1, then 1 plus 1 is 1. And finally, if we have A plus a not A, then that is always going to equal 1. Because if we say that A is 0, then what we're actually saying is 0 plus not 0, which is 1, which equals 1. And also, if we change that and we say that it's going to be 1, then what we're actually saying is 1 plus not 1, which is 0, again, equals 1. So we can do something similar if we are looking at the AND logical operator, because we know that 0 multiplied by 0 is 0, and 1 multiplied by 0 is 0, and vice versa, 0 and 1, and 1 multiplied by 1 equals 1. So again, we can start to throw in some algebra in there. So if we say that A multiplied by 0 is always going to equal 0. Okay, so the reason for that is if A is 0, then 0 times 0 is 0, and if A is 1, then 1 times 0 is 0. In a similar way, we can also say that A multiplied by 1 is always going to equal A. The reason for that is because if A is 1, then 1 times 1 is 1. And if A is 0, then 0 times 1 is 0. So you can see that they match up. So A is 1 and A is 0. We can also say that A multiplied by A, again, always equals A. Because if A is 0, 0 times 0 is 0, and 1 times 1 is 1. Okay, so it's always going to match up. Finally, we can say that A multiplied by a not A is always going to equal 0. Okay, so the reason for that is if a is 1, then we do 1 times 0, because it's a not 1, which is going to equal 0. And if a is 0, then we do 0 times 1, because it's a not 0, and that's always going to equal 0. So that rule works. Okay, there are more rules that we need to be aware of. So one of the rules is that a dot b always equals b dot a, and a plus b always equals b plus a. Now this is a fairly obvious one, even though initially it looks a little bit stupid. If we say that a is 2 and b is 5, if we say that 2 times 5 is the same as 5 times 2, which of course it is, okay, they're both equal 10. The same with plus. If we do 2 plus 5, it's always going to be the same as 5 plus 2, okay, always going to equal 7. So that rule kind of makes sense. Okay, the next rule, again, it looks a little bit daft, but it does make sense. So we say a double complement, so a double not of a is always going to equal a. Okay, so if we say that a is 1, so we've got a equals 1, then a not a is going to equal 0. So a double not a is going to equal 1. Okay, so a double not, a double complement always equals the original a. Okay, the next rule, starting to get a little bit mathematical now. A, b plus c, in brackets, always equals a multiplied by b plus a multiplied by c. It's getting a little bit confusing. This is when you need a degree in maths. So if we say that a is going to be 1, b can be 0 and c can be 1. Now you should be able to replace these because this rule will work anyway, so you can have a go at swapping them around and see if it still works. We can say that 1 multiplied, because that's essentially what we have here, 0 plus 1 is always going to equal, and we'll put these in brackets, 1 multiplied by 0 plus 1 multiplied by 1. Therefore, if we go another step down, if we simplify that, we know that 1 plus 0 is going to be 1, so we need to do 1 times 1, and that's always going to equal, if we sort of work these out, so 1 times 0 is always going to be 0, and we're going to add that to 1 times 1, which is going to be 1. The answer for that, 1, 1 is 1, and 0 plus 1 is 1, so we can say that that rule works. So the next rule looks like this. We can say that a plus b multiplied by c is always going to be equal to a plus b multiplied by a plus c. So we'll stick with the same example numbers as we used previously. So again, like you would do in maths, we can say that 1 plus 0 times 1 is going to be equal to 1 plus 0 multiplied by 1 plus 1. So if we start to simplify that down, we have, well, 1 times 1, 0 times 1 is going to be 0, and we have our 1 plus 0 over there, and then 1 plus 0 is going to be 1, and that's going to be multiplied by 1 plus 1, which we know is 1 due to the something plus something rule. So we have 1 times 1. So over here we now have 1 plus 0, which equals 1, and 1 times 1, which equals 1. So this does balance up. Okay, even more then, we have a plus a multiplied by b always equals a. Okay, so if we say that a is 1, and this time we'll have b as 1 just to mix things up a little bit, then what we have is 1 plus 1 times 1 equaling 1. So if we simplify that down, 1, 1 is 1. So we can then say 1 plus 1 is always going to be 1, and we know that something plus something is something, so that would equal 1, so that rule again matches up. Okay, so there are a lot of these. A multiplied by A plus B, again, is always going to equal A. So what we can have is, if we use A as 1 and we'll have B as 0 this time again to mix it up a little bit, we can say that 1 multiplied by 1 plus 0 is always going to equal 1. 1 plus 0 is 1, so 1 times 1 has got to equal 1, and 1 times 1 does, so 1 equals 1. So again, this rule matches up. It's just going to be a case of remembering these, unfortunately. Okay, this is where it starts to get a little bit ridiculous. They're getting even longer. So A plus B plus C equals A plus B plus C, which also equals A plus B plus C. Okay, so if we say that A is going to be 1 and B can be 0 and C can be 1, then we can put those in just to sort of make it look less like English and more like maths. So we can say 1 plus 0 plus 1 is equal to 1 plus 0 plus 1, which is equal to 1 plus 0 plus 1. So if we start to simplify that, we know that this 0 plus 1 is going to be 1, so we're going to have over here 1 plus 1, which has got to equal 1 plus 0 again, which is 1 plus 1, which has to equal 1 plus 0 plus 1, so essentially, again, 1 plus 1. Okay, so you can already see that this is going to work out. We therefore have 1 equals 1 equals 1. So again, this rule works out. Okay, this is the last one, I promise. So if we have A multiplied by B multiplied by C, that's going to equal A multiplied by B multiplied by C, which is going to equal A multiplied by B multiplied by C. So we could maybe have A equaling 1 and B equaling 0 and C equaling 0 as our sort of sample data to show that this works and how it works. We can start to replace it. We can say 1 times 0 is always going to equal 1 times 0 times 0, which is going to equal 1 times 0 times 0. So we can start to simplify that. 0 times 0 is 0, so 1 times 0 has got to equal 1 times 0, which again is 0 times 0, which has got to equal, well, these are both 0, so it's again 1 times 0. And as you can see, all of these are going to match up because 1 0 is 0, no zeros are 0, and again 1 0 is 0. So, hopefully your brain hasn't exploded, and those are all the rules that you need. And just if you thought that things couldn't get any more confusing, then they all have different names. I'm not going to go through all of these again. If you want to have a look at these names, then pause the screen now. And there are even more for the other ones that we have discussed. So, good luck in learning them all. Hopefully they will all make sense the more and more you do of these. And if not, don't blame me.